will wait several minutes. Okay, maybe I should start. So, last time we studied topological theory of a very special type. So the type was like this. We had fields, let me call them phi, and pi. So these were like maps. And these psi's were like their superpartners. and there was Q that was basically the RAM operator on the space of fields that I will symbolically write as and there were also extra fields pi than P, and Q was extended to the RAM operator on the space of fields and equations of modes. So that's what we studied last time. And we had example number 1, where we had a maps from interval to manifold. And we had example number 2. And example number 2 were maps from the Riemann surface to X. It turns out that we need to have more Qs. In order to get more Qs, we will study a procedure that is called the RST gauge fixing. And we will have extra Q. So it is our goal number 1. Our goal number 2 would be to study so-called twisting. And that also will bring us Q. And later we will unify all these Qs in a single framework. So this is our plan. But let us start with the point A. Suppose we have S that depends on field phi. And suppose there is a symmetry. Phi that being applied to S gives us 0. It is possible to rewrite it in the following form. Suppose we have several things. For each symmetry, we will produce a field CA with a parity opposite to symmetry. It means that if symmetry is even or normal symmetry, then C is odd, and vice versa. Then we can try to write down such effect. However, this action does not solve BV equation. It would solve BV equation if we add here the following term. Six star is an empty. So SDV is what? It's a function of star shifted by 1. And here we have original manifold x times g shifted by parity by 1. So this is the algebra of SIMIS. And assume that VA, VC So this is kind of a standard formula in BV. What's interesting is that naively we may try to integrate SDV along Lagrangian manifold pi star equal to 0, p star. So forget these terms. However, it would be a bad choice. First of all, because of the symmetries, integral would diverge. Second, in the case of even symmetries, we have odd variables, and if we close this term, we will have 0. So naive choice of integration is not nice. It means that we would like to take another Lagrangian submanifold that I'll call LF. LF would correspond to gauge fixing the symmetry. So symmetries go like this, and we would like to cut them by equations F alpha equal to 0. So that's the condition on field phi that you would like to use. Now, if F alpha equals to 0, it means that phi star equals to 0 is not a Lagrangian submanifold anymore. The proper Lagrangian submanifold would correspond to motion of these phi's. And let me tell you what this motion is. So phi star would be equal to B alpha, and here I'll write DI F alpha. Let us check that this is actually a Lagrangian submanifold. To check that it is actually a Lagrangian submanifold, we need to do the following. We need to evaluate. I will do it. Form B phi I star B phi I on this submanifold. Is this. So I'll write it as delta B alpha B alpha here. BF alpha or phi I. And here I will have delta phi I. So here I have variation. But F alpha equals to 0. That's why it is 0. Okay. It is a nice Lagrangian submanifold. Now I still want to put P star equals to 0. So I cross this. However, I am keeping the last term. So that's what I have. And I am integrating here over phi restricted to F alpha equals to 0 over C field and over B field. But now let me do the last step and let me write this restriction in the integral form. So I will introduce H alpha. That is Lagrange multiplier. for equation f alpha equal to 0. And I will get the final form. So this is the action that I'm going to put. I'll call it B or T. To exponent. Here I am pretty satisfied to see the same number of B's and H's. They have opposite statistics. So that's why this measure is canonical. And here I have dphi and dc. In some sense, I'm satisfied because I have this space with coordinates phi and the group and the algebra with coordinates c. These coordinates are odd. That's why superdimension of this space is dimension of the manifold minus dimension of the algebra. And this is a way how to take a quotient. And here I have this exponential. Now, what is nice about this exponential? Is that there is a Q symmetry called QPST. That acts as follows. It takes B into H and it also takes phi into V of phi and here is CA and plus 1/2 CACB FABB V over DC. And you may check that this QB raised T minus to 0. So without this term, it was obvious, and this term doesn't really matter. Now, let us have a look at this term. What's important is that this term is Q beer with T exact. The wavy term is Q beer with T applied to what? Okay, so I'm not careful about signs. So let me try. What if I try B alpha FL? First term gives me what I need. Because it acts on B. Now the second term gives exactly the first term in the wavy line. So F dearest is S plus Q dearest applied to the alpha FL. So what did I found? I found another differential Q. I found another Q that squares to 0. Now I would be able to construct topological theory out of it. How theory were topological here? They were topological because here I had the action that was Q of something. And the metric appeared here. So the dependence of the metric was Q exact. Now, here I have similar phenomena. If metric appears here, and this is metric independence, I'm getting topological theory. So now let me mention the most famous theory of this type. so-called Chern-Simons theory. Consider three-dimensional manifold M. Trivial bundle over with Russian roots G capital. So connections would be one form. With values in three algebra. And I call them A. Then I can write as Chern-Simon in the following way. So what is A? A is one form with values in the algebra, and I understand this algebra as an algebra of matrices. And here I take trace. So this expression does not look, and here integrals over M3. Now this expression does not look as a gauge invariant. However, there is an exercise to check that if delta A is d epsilon plus I epsilon commutator, so then delta A is actually d of something. Homicide. Find this something. Now, this expression, this S Chern-Simons, does not depend on metric. However, it's a gauge theory. So, in order to treat this theory, Chern-Simons, we need to do a gauge fixing. Here is Feynman's gauge fix. And here we will have appearance of something. And that's why we will get dependence on metric that would be QB raised T exact. And this is exactly the condition of being topological theory. Let me give another example of theory of the same origin. Consider two-dimensional Young-Mills theory. Being Young-Mills theory, it has an action F star F raised. And people put here 1 over G naught square. Two-dimensional one. It is possible in this theory to go to the first order formulation. As Young-Mills first order is here phi is a scalar. With the values in G and F is of course VA plus A squared. H small is a two-dimensional number. Now this first order formulation goes to second order formulation if we exclude phi by integrating it out. However, we can do differently. What would happen if we take G naught square and tend it to 0? We will cancel this term. So here we will get a topological theory. Because action is topological. It's not a coincidence that we are getting this theory. It is really related to Chern-Simons theory. Relation is the following. Consider M3 as and 2 times S1. They equal field independent on coordinate on S1. Take A0 equal to 5. Home assignment 2. Show that certain assignments lead to two-dimensional units on and 2 with inner square equal to 0. Okay. So now we will have a break. So I explained BRST gauge fixing and how to get extra Q. So if you have questions, I'm ready to answer.
Yes, excuse me.
Yes?
Here, phi is scalar field with values in G, but A is
One form
value in
in G.
So one form is the same as the scalar field.
No. One form is not the same as the scalar field. A is a mu dx mu. But it also takes values in G.
So you mean this A just has one component A0?
Yes, so A has one component. However, there would be also A1 and A2. So 0 is the component along S1.
The reason you call it a topology theory is
because it's metric independent.
yes.
So dependence on metric is, so the reason, once again, let me pronounce it again and again. So theory is called topological if its dependence on metric is Q exact.
But you also call this term, the first term is topological plus
Yes.
QBRST something is
yes.
also topological.
So so this term is obviously topological because it does not depend on metric. Second term may depend on metric and actually depends on metric, but its dependence on metric is exact. So that's why totally the action depends on metric in a Q-exact way. The first term do not depend. The second term depends, but in a Q-exact way.
The Q-exact way, this Q refer to this QBRST.
Yes.
It's not the original some other Q.
No.
Corresponding to S, but corresponding to new.
So it was a gauge theory. So being a gauge theory, it has this symmetry. Having this symmetry, it has, in order to treat this theory, we involve ghosts, BC, Lagrange multiplier, all this business, and have this Q. And the same happens for two-dimensional Young means at zero coupling. It is a non-trivial theory. Even at zero coupling. Because here we have phi plus a squared. It's not a quadratic theory, not a Gaussian. So let us have a break until 16:30 as always.
你要看从什么角度看，这是直接构造不一样的就是随便。
然后他说这个这一定是一个 topological theory， 这 action 这样子看是 topological theory，
它跟 M2的 match 没关系。
就是它这里面 F 是跟 match 有关系，因为和上头的一样，就是 A 也跟 match 有关系，就这个 F 也有一个
A 为什么
A 是跟 match 的 connection， 在那个 match 的一起跟 A 是的。
不，它这个 collection 是它那个 triple bundle 上的 collection， 跟 match 没有关系。它 triple bundle 它跟 D group 它跟那个 D group 有关系。
它不是底空间上，
是那个 bundle 上的，
它的 bundle 上的
是一个
它跟
额外的 bundle 上的一个 connection。不是，就是那个第一项是一个跟 match 有关的项的原因是什么？
因为你里面没有 G 啊。 没有 G，
没有 G，
那个 match 的那个 G，
这个
这个 A 肯定跟 G 没关系，是你人选的一个 collection。collection 它有很多个嘛，你随便选一个，肯定跟 match 没关系。如果它是依赖 match 的，那我给我一个 match 我就被定出来一个 collection，那个叫 ASZK collection。这个 A 不是 ASZK collection， 它是另一个 collection。
然后他把那些 match 的那些东西都放在 QBST 这个东西里面，对吧？然后
它那个是沿用前面那套做法而已，直接加上去的，所以它里面有可能跟 match 有关系。
对，然后他说是长这个样子的一个东西，反正是会整体跟 match 就是他说这个 series 是跟 match 没关系的，含义是
前面那项没关系，
前面讲什么，但他加了那个 QBST
可能有关系，
但是他还叫它同了这些。
他是这样叫它就。
我觉得是因为后面那项它是 QExact，
所以它 QExact 的它之后就会导致你对这个 action 积分，
对
因为对 action 积分以后感觉就像是没有 boundary 的那个contribution， 就是因为这个 QBST， 所以就像是一个斯托克斯定理一样的一个东西。但为什么那个积分和这个 QBST 是配套的？
对，这个 Q 它不是 D 呀，它是为什么它最后不会贡献？不会导致它不脱？
这感觉是这个 QBST 和这种记各种场的这个积分是配套的。
是配套的 ，Q 其实就是 D， 它只不过不是 M3 上的 D， 它是它那个 tangent bundle shift 1上。
看一下这 Q 的，
它 Q 是 X 上那个
Q 的定义是啥来着 ？Q 是 act Q
是 X 上那
，act 到某个东西。
你们先把它 X 上这个东西啊。对，它 X 上这个东西是它写的。Q X 上这个上面，但这里的积分是只有 M 上去。
就那四个 capital D 的积分哦。
对。
然后那四个 capital D 的积分，现在意思就是你后面记一个 QExact 项，会得到零。
为什么？
你的 QBRST，Q 是这上面的 differential。
Q 是这上面的
differential，
就完全对应它上面的对吧？
这个
它应该不叫 drop， 它就是上面的一个 differential。
一个什么样的一个？
就 Q 是它上面的 differential， 所以这是什么意思呢？
它
对，它可以 QX 到 B 上是得到 H，
对
，X 到 phi 上是得到 C 一样。
对。
就像是在这个四个变量之间，就是不 QX 到 B 上是 H， 就像是做了个 Dirac differential， 把那个 B 变成了个 H， 就是 dx， 就相当于 B 是 X， 把 B act 一下变成 dx， H 就是 dx 那个 odd variable， 就像变成 perceive。不是有那个 x 被 Dirac differential 一下变成 perceive， 对，然后它这个 act 到 phi 上有一个 c， 这个，所以
三项的意思。
对，第三项没什么意思。
第三项是这个上面，这个是这个上面，
对，
是第二个东西。一直看前面两项好像就是。
为什么要凑个第三？第三项为了说它是个 differential， 平方等于零，
我觉得应该是的。没有这个。
好吧。神奇，就是他要凑个二次项才能是它的平方。
可以说写这个区的网都没事儿，区网没有事儿，总会有大区算上。
区网他大概想说的是什么？想说的是只有一个 chart。
我不知道。 那去了会有当 true 的 smart 去了会有一个 global 的 stack
global 对，可以应该是有 global section 的。
不够吗？你N为方你要有 N个够，还有ASZK。
对，它应该是一个 chart 的意思。对对，N 感觉是感觉是 N 的话是 N 个 section， 然后分成一个 global 的 structure group。对，他问了一个，我也很confused那个问题，就是这个方程为什么会有 structure group？ 往往不是希望得有2个 chart 才会有这个转移函数，才会有这个转移函数要用一个矩阵来衡量一个矩阵可能在某一个。
我觉得他的意思就是它是记法，就是它的帮手上面是一 group，
应该就是一个多记方，然后associate的一个这个占子方，但是奇怪了，看不起。这应该不能叫它的 smart。
哦，是 principal 及 bundle 上面有一个 trivial 的 associated，
有一个associate bundle 应该是。
哦。OK，
最近有写讲义吗？
没有写讲义，
该写了，
写啊，
我一写一写嘛。
OK， 可以思考一下，
正好可以把这些写。
哎，我们后面我还没查到什么，他为什么叫我们去，我俩去一下。
哦，他是想做采访，SIMIS想做采访。他
为什么叫他？
哦，跟他没关，跟 Losev 没有一点关系，只是因为他之前他是前段时间做老师的采访，我去帮助采访过一次，现在做采访去了。
我们俩要的样子。
不知道，因为上次他找我去采访，他问了我可不可以，我说可以，然后他直接来跟我说你们俩，说我跟你一起采访。他跟你说过这个事吗？他没跟你说过。
你要被采访，
他们问我，
他没问，他完全没问我。
你要被采访吗？
对，要被采访。
他采访我，我采访他。
我知道，肯定确认说。
对，肯定确认。
如果要找个人来采访你，他们还得出一个人来采访你。
但是我感觉找个老师来采访我也不太好。
对，
确实吧，
所以就只有我来采访你。
反正很诡异。
那个 S1 上的杨 news 为什么是个3次项目奇怪
？S1
一般我们说杨 news 不是一般长成
哪个 S1 上来的？
那个叉叉前面。
叉 M2。啊？
对。
M2 乘 S1。
对啊。
这里。哦，这里。
不是。这个3次，
一个是2次，2不是2次了。
他说考虑那个 A 的话是3次，
但是他没有，他这里的 A 始终是1次的，他这里 F 是2次的，那个 phi 是0次的。
phi 是，
因为它是那个，你可以理解为那个 dx 前面的 component， 它不是 phi dx， 所以它是1次。
所以。
它是0次的，所以整个是2次。
然后他说这是一个 topological theory， 然后你说的意思是理由和上面是 topology， 第一项 topology 的理由是一样的。
对。
它后面打个叉是什么？
它取其名，然后取相语。
哦。但是这个里面完全没有那个什么 gauge fix 的问题，有问题吗？
他还没想gauge fix， 你要得引入那些项之后再考虑。你先引入一些 IT field， 然后再考虑gauge fix。
就是他现在只是说有这么一些个本身就是拓扑的理论，
对，
我们后面可以考虑加上一些乱七八糟的东西的，作为一个这个理论的一个 gauge fix 之前的样子，还是叫 gauge fix 之后的样子，还是之前的样子？就加了一些乱七八糟的。
我觉得它逻辑是这样的，它本来那个分盘不说有什么gauge，它可能本身有gauge，但是不影响它本身gauge。我们先把它扩展到它含有 anti field 的版本，然后在有了这个更宽广的地方、更大的理论之后，再考虑它的那个 gauge fixing。它 gauge fixing 可能做出来的最后面跟之前完全都不一样了。
这个 SIMIS 这个我不看后面的 Q 什么项，就看前面这一项，它是 gauge fixing wall， 这什么意思啊？什么叫 gauge fixing？就是 integrate over G 还是什么？就 integrate over metric 还是什么？就是我现在已经可以 dependent， 所以应该是 gauge fixing 做的是吧？还是没 fixing？
应该是 fix，看你怎么看，
什么叫 gauge fixing？
因为你上面有个你 group key，站在上面是 invariant 的，对吧？你选一些那个什么，所以选一些代表元出来，它就算是个 fix，它是不
一的代表。
大题 capital T。
就是如果你的轨道也放到积分里，可能会发散，所以你只选轨道上一个点，然后你固定这个点就叫 gauge fixing。
我这个积分里压根你没有积过轨道的，只有积了整个 M3 就是轨道代表。
因为你还没做 pace integral， 你 action 肯定是那个 action 是 finite， 但是你的那个 pace integral 可能是发散。
就是我的 path integral 那个上面我需要在一些 orbit 下去看那 orbit 的积分，而不是积整个的。但这个 orbit 的积分，他说那个找一个 Lagrange submanifold 积一下是一个意思吗？
对
，orbit 就是 Lagrange submanifold。gauge fixing
你说 orbit 是
就你前面说我要找个他们找定期的 orbit， 就是orbit 每个 orbit 你找个代表人就要去加，每个 orbit 找个代表人这么去加和找一个 Lagrange submanifold 来做是一个意思，就是把它的 fiber 全部都看成一个 base 上的点。
其实是差异几个一些。
是的，
就是把整个 fiber 压到它这个 base 上一个点，就像是一个类比于一个 orbit 上面取了一个点这个概念。
就跟你那个在 fiber 上取一个 section 差不
多。原来这个叫 gauge fixing， 就是取一个 section，
对，
这叫 gauge fixing， 在这个整个 simplex all 的 symplectic 这个 manifold 里面取一个section， 它这个 all symplectic manifold 是一个bundle 这个样子，在这取 section， 取一个，它看上去像是个 tangent bundle 什么的 ，cotangent bundle 之类的，但是在 cotangent bundle 取一个 section， 这个 section 正好和底流行为一样，正好一半的这个 cotangent bundle 是，这个东西它叫做一个 gauge fixing， 然后也正是你说的那个每个 orbit 可以取一个点，怎么去加，
都可以这样，差不多。
orbit 为什么一个 fiber 是个 orbit？
因为我说的他跟我说，选作用在上面，
起作用在这个 fiber 上，是吧？这个 fiber 感觉那个便利里面。我感觉是做哪里的？跟这个 phi CBH 其实做在什么位置上？
大题。
对 ，C 感觉就是吉利的元素。
对，这是 algebra。
对，所以
这个2/3是什么东西？
就是一些系数，
为什么要写个2/3呢？突兀的。
为了某些，就是一些人为的那个嘛，写1/3很好理解，因为你修导之后它就只有1了。
对对。
然后二我不知道为什么，
所以知道那个这个化学挺卫生挺好的，说那个什么，是跟个什么 index theorem 什么有关系？这个四川这里必须是3/3才行，1/3它不是一个头的 invariance。 不是乘4这个东西，必须是2才行。
但如果这里是2/3，
就它需要这个东西 encode 的一个 symmetry 长得像这样，就 delta a 有一个 a 变化一下以后，你整个东西是不变的 ，yes 是不变的，还能差了一个 d 什么东西，所以你记起来不变。
哦，
Okay, so let me continue. So we covered the first one. There is the second one. So let me say in advance that these examples would be particular case of the second one. So relations would be as follows. So there is Mathieu-Quillen. Mathieu-Quillen would be particular case of twisting. And then there is a separate, like BRST. Looks a bit mysterious. But later on, we would unify all them in a single framework. Okay? Now, what can I say about twisting? And what it is all about? Another source of Q symmetry from supersymmetry. In supersymmetric theories, there is an algebra of symmetry that, roughly speaking, works as follows. Q alpha Q beta dot is P alpha beta dot. Or gamma alpha beta dot M Pn. So Pn's are generator of translations. So now let us have a look at these Q symmetries. First of all, there are too many symmetries. And second, they are not scalar symmetries. They have index. So they are not on the curved space. But there is a way to cure this problem. By changing the dimension of fermion. Suppose we would cure this problem, and suppose Q alpha would be scalar. This relation is a relation for charges, but we need relation for generator of charge. In particular, it could be that energy momentum tensor is Q of something plus V of something else. In this case, generators of translations would be the same, because generators of translations are integrals of energy momentum tensor. So this is necessary but not sufficient condition. So keeping this in mind, we may start exploration of the so-called 2,2 supersymmetric models in B equals 2. They have the following action. So left and right means left moving and right moving. Left moving means that on equation of motion they do not depend on z bar. And right moving means that they do not depend on Z. Interestingly enough, this model has the following symmetries. Left symmetry generated by 1-0 power. Left supergroup. There are two of them. Of course, they are made out of boson. And the fermion. And I have two combinations. And let me call this combination somehow. Let me call this combination, say, G plus. And of course, I will assume that it is left. And also G minus. Once again, from the left fermion, however, with anti-holomorphic index. I call them G because it's standard notion for them. Okay, I put L just for you to know that they are left moving. And they have similar formulas for the right moving. Okay, I will G plus right mover. I would like to keep all of these formulas. So written like this, all of them are. So these have dimensions 3/2, 0, and these have dimensions 0, 3/2. Let me explain why 3/2. It's because this left has dimension 1/2, 0, and this left has dimension 1/2. So that's why altogether this has 3/2, 0, and this has 0, 3/2. Now, my goal is to make a scalar symmetry out of it. And I actually have two choices. First choice is the following. I will go for the color chart and underline the fermion that I would like to make scalar. Suppose I want this fermion to be a scalar. And this fermion to be a scalar. And let me call it the red choice. Then what happens with the fields? G plus left integrated over the contour encircling point 0. And I put field phi I here. Would give me psi I left because of this term. So red choice means not only I take these fermions. Red choice means that I combine this with this. Similarly, integral of g minus right of z, I may call it z bar. So what I actually see here? I actually see that red choice acts like here. And this is the so-called A twisting. Now, what I need to check? I need to check that energy momentum tensor. If energy momentum tensor is Q exact, so what is important with this type of twisting? Now, the energy momentum tensor is for bosons plus there is a term for fermions. So interestingly, term for fermions looks exactly in the following way. So it takes phi left with the d I j bar. Now once again, to remember what happens with another fermion. Okay, so another fermion is still here. So after I made this twisting, and this psi left became a scalar, the second fermion got dimension 1, 0. Okay, we need to check if energy momentum tensor is exact. So how do we do it? We take G, and here we have our G. G left plus, and apply it to something to get energy momentum tensor. So what can we put here? Most probably we would like to put here a similar expression. Something holomorphic, but involving field psi left with the bar. Now, there is a home assignment. Home assignment would be to check that, okay, I will try to explain how to do this home assignment. That the integral over z around gamma naught applied to this object is energy momentum tensor. So it has a proper dimension. This has dimension 1, 0. This has dimension 1, 0. So what else? What else can you get? But you need to make contractions. So home assignment proven. And this is the twisting of the type A. Actually, twisting of the type A turns out to be exactly Mathieu-Quillin formula. So how to see it? Where should I write? I will write on this board. Statement. I'm keeping twisting. listing is equivalent to Machain. At first sight, actions are different. However, if I make relabeling of fields, if I relabel psi L, J bar, G I J bar, if I label it as phi R, I need to make psi R J bar. And if I relabel psi R J bar G I if I call it 1 second. 1 second. I R. If I call it by J bar, yes. Then action would take the form J bar, I, J bar, by J bar plus the bar. Then the action will take this form. Now I can go to first order formalism and understand it wavy term. I consider J bar as a constant. And then C is this term together with this term. This is Mathai equivalent term. And this is also term that we had in Mathai equivalent formalism. So here we see, so this term is e to the Lagrange multiplier times function, second term, so it's the first term. The first term. Second term is PEF, and last term was epsilon T squared. So this is what we had in Matai-equivalent formulas. And here we have exactly these terms. Okay, so it means that red choice did not brought us anything new. So I confirmed that Matai-equivalent is inside twisting of type A. But there is also twisting of the type B. And twisting of the type B is the following. I will take another chalk and I'll keep this convention. It's a blue choice. So this is the scalar, but now I would like to consider this also the scalar. So my new choice would be to take this to SIMIS as scalar SIMIS. And that is B twisting. Now then the question is how B twisting is acting. Okay, now I will erase this board. So the second term acts as before. However, new thing happens when we study the first term. Because G minus left plugged on phi bar, I bar, gives width. So totally, Q applied on phi bar, I bar, gives so Q actually acts as Dalbo differential. And now, of course, there is extra assignment. There is an energy momentum tensor, say T left, that equals, of course, d phi bar I j bar g I j bar plus now the question is to check if this is Q of something. There is no problem in the right sector because nothing changed. But there is a question on the left sector. So fourth assignment, find this something. So totally we see that in the so-called B twisting, Q is acting not as a Durand differential, Q is acting as a Dalbo differential. And moreover, there is an object that is Q closed. So this is the P model. Here I need to tell you some tricky thing. Energy momentum tensor for bosons is always G bar, d psi I, d psi j bar. However, energy momentum tensor for fermion depends on their spin. And here is the trick for you to know. It is D, and here there is a scalar fermion. And here fermion that is 1,0 forms. So that's why computation is not always exactly the same. I wrote you correct formulas, but you need to keep it in mind. Now, why energy momentum tensor is like this? It's because for the scalar fermion, action is scalar. And it is changing by d bar plus ud. And therefore its reaction for change of complex structure is exactly this. If it's not a scalar fermion, then it requires connection and things become a bit more complicated. But this is the rule. I think that in this course, I can just postulate it. That energy momentum tensor, so if you have a scalar fermion, then energy momentum tensor goes like this. Okay, I'll put your AB, and you put A and B that are proper. And now I'd like just to mention, so I can make a break, but let me mention what happens in dimension 4. I will just mention it. And we will not go into much detail. There is a gauge field. And we may impose as Mathieu-Quillen equation self-duality. So what does it mean? It means that there is F, that is dA plus A squared. And the equation means that self-dual under host tau part of curvature vanish. So how do we do it? Let T plus self-dual to form. Then in Mathieu-Quillen form, I would write plus, okay, and let T plus take also values in the Lie algebra. And here I'll write trace P plus F. So it's Mathieu-Quillen formula. But it's only the first piece of Mathieu-Quillen's formula. We need the second piece of Mathieu-Quillen's formula with fermions. So this is for the function that should vanish, and this is its fermionic counterpart. Let us have a look at this formula. Could we take this integral? No, we cannot, because it has gauge symmetry. And it has very big gauge symmetry. It has bosonic gauge symmetry, acting on A, and fermionic gauge symmetry, acting on psi. In particular, for abelian case, this term is absent, and there is a symmetry psi goes to psi plus d epsilon. So what I am doing in this particular case, I am doing gauge fixing. As I always do. So let me do gauge fixing for the fermionic symmetry. So how do I gauge fix fermionic symmetry? I pick up some condition, say d star psi equal to 0. So let me consider this as a gauge condition. So I add here theta d star psi. But this is gauge fixing. What I need to do, I need to add ghosts. So since this is a fermionic symmetry, ghosts would be bosonic. So I will have ghosts phi bar d star d phi. Actually, with some terms depending on A. And this would be the content of the theory. And this theory has bosonic. And I'm not going to fix this bosonic gauge symmetry. I just want to have a look at this theory. Because I would like to compare this theory with n equals 2. Okay, now I can write this piece. There is a theory that is n equals 2 supersymmetric Young-Mills theory that started all this business. It had a gauge field. It had a doublet, A going from 1 to 2 of fermions, and it had 2 scalar fields. And I would like to compare theory that I got from Mathaei-Quillen procedure with this theory. Okay, being young means theory, it is F star F. Raised 1 over G0 square. But I know how to deal with such structure. I know that this is actually okay. I want to do it in steps. So this is young mix. F star F. Decompose F into F plus and F minus. Star F plus minus is plus minus F plus minus. So this nice piece F plus squared raised minus raised F minus. F which F is F plus squared plus F minus squared. So that's why adding this F by F, I will get so if I add, I'll get 2. Minus 10 that I'll keep separate. Now this term is actually critical value integral over t plus over the exponential of raised t plus plus G0 square raised t plus. Okay, so in this way, I'm making n equals 2 super young means in terms of, so where I have A fields, I can make it into Mathai equivalent form. And now interesting thing happens with fermion. Edward Witten proposed to do the following. He said, there are 2 fermions So there are I will write them in wire notation. Psi alpha and also psi alpha dot. Assume that A transforms as alpha. Then psi A alpha is something like psi alpha dot A. And this is nothing but one form. That we have here. Now, what is psi alpha A? He said, there are four. Here we have four terms. There is eta times epsilon alpha A, antisymmetric tensor. And phi, and here we have symmetric tensor. Now pi, that is symmetric tensor, is isomorphic to self-dual form. So this psi form eta pi system. And it is exactly the eta pi system that we have here. Altogether, we see that Edwards-Witten twisting that he produced many years ago, exactly 40 years ago, is nothing but Bataille-Quillen procedure. So that's how I would like to finish my talk today. And the next time we will start. So I gave you a variety of topological theories. So next time we will start unifying them, as it was promised. Okay, thank you.
没有，但是我的就是我自己本地游戏带的，我给它传上去。唯一还是写一些，因为一句，都不是我需要，因为我确实就是就卡了很久。没关系，我可以把我先写过那个，不然到时候6月份你们要肯定要下底线，那肯定会出的。问题不大，
那你分个工，一个人1周，3个人，3周写一个也快吧？
但是我可以把我多写，我之前正好有写。
我感觉我懂的部分太少，感觉写的很 yes， 你知道吗？ 方可以懂一点的，我可以精写一下。
OK。反正我大概能把做个先跟着可以，我就5一我再刻上去，然后到时候再学。
辛苦了，没有可以refine一下。
到时候我感觉一个人就这帮不能就是一个人站在一起，就感觉就是他们人一起讨论一下，我们应该搞个讨论班来讨论他讲什么讲。OK， 我感觉我自己写着也写不出什么东西来。
我也写不出什么，不知道在说什么。
我感觉补充一下他写的挺好。
就是如果你要是把它版图抄下来，那很简单，但你要想把它整理的像是人话，然后把它讲得很明白，我觉得这个就不简单。
可以先把版收录下。
对，先把版收录下来，让 AI 先学一遍。
对，然后补一下其中那些
所以说都得看我们的要求是什么，让我们写一份非常好的讲 AI 非常好。这是什么样的？
我觉得是至少写了以后会人用的。我觉得应该是这样，不然写这个没意思。
一可能就是
按你们学，
可能跟你们博士论文有关的话，可以直接放进去。像这种如果
有关
跟你有关的话，
有关的部分我们自己都
自己写完了呀，有关都自己写完了，对。
但可能这个跟这个课它又拓展了一点跟你没有关。
是，那他课里总是能讲些不一样，
所以可以把它放进去。那我这跟我的其实没什么关系，目前看不出。
所以看吧，要是有精力的话，我找天每周什么找人讨论一下，一起写。就是那种什么，我拿或者谁拿电脑，然后就是拿大屏幕，就是然后一起讨论真笔记该怎么写，一起看的录像，就是随时等。就我觉得就这样可能会就是真正会有些帮助。但是你要光写笔记，就是你还是光把它抄遍，我觉得有时候我只知道我写着，我都不知道我在写些什么东西。
对
吧？到时候看有没有谁的经历给他们组织一下，这样，我觉得这样写笔记有帮助。
对啊，这个感觉要补充很多东西啊，这写个笔记。对，
所以说一人写，一人分，就是大家分开写，就是每个人只能学到一点，但如果大家一起写的话，就是可能都能学到的。
对。
而且他讲的很多，他其实也是挺连贯的，没有分散，每个都有真的有关系。
但是我觉得上课的时候已经把我说晕了，不知道他在说什么。
所以就靠我们3个4个还是几个人？算路易斯。
我觉得也应该算吧，算是4个吧。
理想情况下是可以找个时间一起讨论、一起写，然后差不多1个下午能写完1节课。但是这样比起来质量会高一点。对，主要是把这事情讨论明白，而不是把它打出来，这个很简单。
对，我准备再看一下，因为他现在到目前为止，我不知道他说什么，所以我可能没有能够。
BV 的部分，我可以给你们讲明白一点。
OK。
因为就是我们最近写文章，他给我留的一些主要讨论问题都是这些东西。
对，我觉得就到目前为止，都对我来说太抽象了，我不知道他说什么。
我就从之前在上次那个在先讲 TQFT， 然后讲什么 Cycling Formula， 然后我从那块开始 lost。
我觉得那块可能路易斯熟一点。
路易斯你熟吗？
我这不能
啊。
我最近又在做 A model。
对，所以。